In Algebra 2, we talked about a bunch of things called parent functions. They were very basic functions that we would transform around the coordinate plane based off of some information in the equation. Some of our basic parent functions were functions like the constant function. You might remember from your science classes that constant meant it doesn't change. It doesn't go up, it doesn't go down, it remains constant. And for us, the constant function is a horizontal line. And it doesn't have to be through y equals 3. I just gave an example. It could be y equals -5. It could be y equals 100. The other type of parent function that we actually worked a lot with in Algebra 1, the identity function. The identity function is the graph of y equals x, and y equals x goes through some very special points. It goes through -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and so on and so forth. It's linear, it has a positive slope, but we could take that line and we could move it up, down, left, right, we could change its slope, and it was still a straight line. Then in Algebra 2, we spent a lot of time talking about polynomial functions. And two of the most common polynomial functions that we work with were y equals x squared and y equals x cubed. When we spent all of our time talking about quadratic equations, we took that parabola and we moved it around the coordinate plane quite a bit. And then we did a similar thing to the polynomial functions when we got to things like y equals x cubed and y equals x to the 4th. At some point in time, we reached something called the square root function. The square root function was actually the inverse of the quadratic equation. It looks like a sideways half of a parabola, and it's the equation y equals the square root of x. It goes through points such as 0, 0, 1, 1, 4, 2, 9, 3. What I did was when I made this table, I chose numbers for x that I knew I could take the square root of without getting a decimal. We also talked about the absolute value function. We reviewed absolute value graphs in chapters 1 and 2. Absolute value graphs are V's. The reason they end up being V's is because when you take the absolute value of x, you always get a positive number. So all the outputs have to be in the positive y-axis region. Some of the ordered pairs that lie on this graph are -3, 3, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. At the very end of Algebra 2, we started talking about something called rational functions. Rational functions were one where the input, x, occurred in the denominator of a fraction. The parent function of the rational functions was y equals 1 over x, and it had two halves of a graph. They were called hyperbola. What we're going to do is we're going to do translations on the parent functions. This is a review from Algebra 2. So when you added a number to an original function, that would move the graph up this many units. So for example, let's use y equals x squared because that's mostly familiar to us since we spent so much time in Algebra 2 talking about y equals x squared. If I do y equals x squared plus 4, because I'm adding 4 to the original graph, that parabola moves up 4 units. And if you subtract a number from the original function, it's going to shift the graph down that many units. So if I did y equals x squared minus 9, that would shift my parabola down 9 units. The shape of the graph would look the same. Its vertex would be in a different location. We could also shift graphs left and right. This was a shift to the right. And in Algebra 2, that probably confused you because the right is the positive x-axis, but it said x minus c, so a lot of students want it to go to the left, and that's not how it works. So the graph of y equals x minus 3 squared would be that same parabola, but it would be moved to the right 3. When we move to the left, there'll be a plus sign, and this will move the graph to the left. So if I did y is equal to x plus 1 squared, that would take the parabola and shift it to the left one. Another thing we did to the parent function was we reflected it over the x-axis. We sometimes call that flipping it upside down, but the appropriate term is reflect over x-axis. So if I did y is equal to negative x squared, that would be that same parabola except upside down. And then we could do many translations all at once. So we could use all of these at some point in time. We could move a graph up to the right and reflect it all at the same time. Now, why did we care about the translations on graphs? Because if you memorize the parent functions, which is what we would like you to do, you'll be able to draw very quick sketches of what graphs should look like. So here's an example of what we'll ask you to do with translations. If I give you the parent function f of x is equal to x cubed, and I ask you to describe the graph or describe how these two functions are related, because this one is the parent function, the second one is just translations on the parent function. And the translations are that it's been reflected over the x-axis, it's been moved to the left 5, and it's been moved down 4. So if I have a quick sketch of y equals x cubed, I'm going to take the center of the graph and I'm going to move it left 5 and down 4. And then I'm going to flip the graph over, so instead of going up from left to right, it's instead going to go down. So there's a quick sketch of what the graph of f of x equals negative x plus 5 cubed minus 4 looks like. Sometimes we multiply a function by a number. If the number you multiply is greater than 1, this textbook it expands vertically. Different textbooks use different terminology for what happens when you multiply a function by a number. Sometimes they say that it stretches vertically, so you may have learned that in Algebra 2. So for example, if I use the graph of y equals x squared, which looks like this, the graph of y equals 3x squared stretches vertically. In other words, it becomes narrower. The other thing that can happen is, what if the number you multiply by isn't greater than 1? What if it's between 0 and 1? Then we say that it compresses vertically. And that may be how you learned it last year. So if I use the equation y equals 1/3 x squared, instead what it does is it makes the graph wider. So now let me tack something onto this equation here. The parent function we're going to work with is y equals x cubed. and we want to determine the translations on the parent function. If I give you y equals negative 1/4 x minus 2 cubed plus 7. Well, this still reflects it over the x-axis anytime you have a negative. However, this time the 1/4, we say it compresses vertically because it's between 0 and 1. It's going to make the graph a little bit wider. It's the number in front of the parentheses is independent of the negative. The negative in front of it always reflects it over the x-axis. This is to the right 2, and this was up 7. The last kind of transformation we're going to talk about is what happens when you multiply the input rather than the output by a number. So if you have a number being multiplied by the input, you're going to see it inside a set of parentheses or inside a set of absolute value bars. If that number you multiply the input by is greater than 1, we say that it compresses horizontally. And if it's between 0 and 1, we say that it expands horizontally. So here's our last example. We're going to go back to our parent function of y equals x cubed. If I have y equals 5x in parentheses cubed, we're going to say because this is greater than 1, it compresses horizontally. So it's kind of like the opposite of what happened when we expanded vertically. And in this one, because c is between 0 and 1, we're going to say that it stretches horizontally. And that is families of graphs and transformations on parent functions.